And welcome to Computer Graphics on this kind of a cloudy Wednesday afternoon. At least it's hump day, right? Oh, and if you're wondering, no one's commented on the on my background yet today. Anybody have any clue? Remember, I'm a George Lucas fan. Anybody have any clue? Those are the cops from THX 1138, robotic cops from George Lucas's first movie. And if you kind of like weird sci-fi, you might want to check out THX 1138. It's very different from Star Wars. It's a very thinky movie, but I love it. It's among my favorite movies. Okay. Alrighty. So we got a lot to do today, so let's go ahead and dive into it. So let's see. So today what we're going to be doing is we're going to be talking about polygon shading. And polygon shading is what you're going to be doing on assignment 4. Okay. Now, what is polygon shading? The idea behind polygon shading is that we are going to take the Phong illumination reflection model that we developed in the last chapter, and we are going to apply that model to a polygonal mesh. So if you go back and you think about like the 20 spheres example that I went through, there were no polygons. We modeled the spheres using the underlying equations for a sphere. So there were no polygons at all. That was actually true spheres that we were rendering. But in reality, 99 point blah 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 percent of the time, we're dealing with polygonal objects, because in the real world, the objects we want to model are too complicated. There's no simple formula for them. So we have these shading algorithms, and shading algorithms are basically, the idea is to apply a point illumination reflection model to a polygonal mesh in such a way as to approximate the object realistically, or to render the approximated object realistically. So the easiest way to see this is just to see it, okay? Here are some spheres. These were actually generated by my version of Program 4. And it's using a low polygon polygonal mesh to represent a cylinder. Okay, and basically I took an octagon and I extruded it into 3 dimensions, rotated it around, and got a cylinder. It's not a very cylindrical cylinder. It's only got 8 sides to it, but it gives you an idea of what you can do. And you can see there are 3 shading methods we'll talk about. We'll talk about flat shading, Garot shading, and Phong shading. Now, Butong Phong was the creator of the Phong illumination model that we talked about in the last chapter, but Dr. Phong also took that model and applied it to polygonal meshes to come up with the Phong shading model. So it's the same Phong, but it's not the same thing. Phong's illumination reflection model is what we've already studied. Applying that illumination model to a polygonal mesh is what's called Phong shading. So he did 2 things. You can do more than one thing in this world. And actually, he did those 2 things pretty early. The poor guy died. I think he had leukemia in his early 30s. So for a computer scientist, that's like right at the beginning of your career, pretty much. Pretty sad. Anyway, so shading has 3 goals. The 3 goals are to give a polygonal mesh a solid 3D appearance. So that's the first goal. The second goal is to decrease the visibility of the polygonal mesh. And the third goal is to realistically render specular highlights. And if you want to look at the three techniques we're going to talk about, flat, Garreau, and Phong, flat shading accomplishes the first goal of giving the polygonal mesh a solid 3D appearance. This looks solid because of the way it's lit. However, flat shading certainly doesn't hide the polygonal mesh. In fact, you might say it makes it startlingly obvious that this is not a cylinder. It is some octagonal shape that's been extruded into 3 dimensions. But Garreau shading does a pretty good job of smoothly of making the surface look rounded, look smooth. Even though it's the same, there's still the same number of polygons here. You're still looking at 3 polygons here. And if you look closely, you can actually kind of see the dividing lines between the first poly and the second poly and the second poly and the third poly. That's called mock banding, and that's an unfortunate side effect of the way Garreau shading works, but it's a hell of a lot better than flat shading. It looks pretty damn good. In certain angles with the lighting, you can see these mock bands. In a lot of angles with the lighting, you don't see them at all. The most complex shading algorithm we're going to look at today is Phong shading. Phong shading, this looks pretty damn good. Remember, it's just an octagonal shape that's been extruded into 3 dimensions. There are no more polygons in this puppy than there are in this puppy. Right? The underlying structure is exactly the same, but we're applying an illumination model, the Phong illumination model, in such a way that this thing looks like a rounded green metallic cylinder. The only giveaway is when you look at the edges, you can see, oh, it's actually a very low polygon count. And we're all used to that. If you play video games, especially older video games, that if the way you want to find out how much they cheated on the polygon count is to look at the edges, because the edges you can't hide with your shading technique. The complexity of the polygonal mesh. It's pretty obvious there that that's a very low polygon count. But if it weren't for especially this edge and this edge here, you'd have no way of knowing that this wasn't actually a curved shape. It looks really damn good. Okay, so how does flat shading work? Well, the first thing we have got to do is we've got to get this cylinder. And as I said, the cylinder is really an octagon, an 8-sided figure that I've extruded in 3D space. Then it helps to know how to compute the vertices, because obviously if you're going to define this damn thing, you've got to find its vertices. Well, there's this relationship here. If x, I made it 100 in mine. If each of the edges is 100, then this y here and here, the y, it gives you both the vertical offset and the horizontal offset when you have one of these angular, 45-degree angular lines here. It's just whatever x is, so 100 over the square root of 2 gives you the vertical y displacement and the x displacement. Yes, they're both called y because I'm computing that from the length of the edge here, which is what I'm calling x. So if we do that, we can quickly generate a table of vertices for this thing. I let x be 100, and so 100 over the square root of 2 is 70.7107. And then I centered my octagon at 0, 0 in the xy plane with a z of 50 on the near end and 450 on the far end. So really, if you look at this, there are 0 through 7, that's 8 vertices, and 0 through 7, that's 8. So you've got 8 front vertices and 8 back vertices. All of the front vertices have a z of 50, and all of the back vertices have a z of 450. So this thing is 400 units long, right? And if you look at the values, you should be able to see where I got them from this drawing, this formula here. So from minus 50 to positive 50 in x. So that's why that's 100. And the y's there are at 120.7107. And then if you come down to this point here, it's 120.7107 50. And that's because, again, this is 70.7107. So I had to add that to my x and subtract it from my y, because my y is going down as I move in this direction. And so that's how you get those values. You can just say, screw it, I don't care, I'm just going to use those values directly in my program, but I wanted you to see where they came from. So for flat shading, the way, now that we got an object, we got to say, okay, how am I going to shade this object, Mike? Well, what I'm going to do is I'm going to compute one surface normal per polygon, and then I'm going to apply the Phong illumination model using that one point on the surface of that polygon, and I'll get some color, some intensity, and then I'll say, I'm just going to paint the whole polygon with that color. So this guy is so bright because it happens to fall in the specular reflection, but there's no subtlety to it, because this fell in the specular reflection. It just shades the whole dang rectangle with that color. Okay, so we've got to get a surface normal. So how do you get a surface normal? Well, we know how to get a surface normal. We've got our points, right? We would need to define our polygons in clockwise order when viewed from the outside. And basically the way I did that is I like start here. This is front 0. So this polygon on the top, you're only looking at it from its edge, would be front 0, back 1, front 1. So it would draw the rectangle that way. And once we have the polygons, we can then get the surface normals, right? Because all you need, we've done this before, it's exactly what we did for backface culling. We computed the surface normal from the first 3 points, right? We created 2 vectors, P and Q, right? And then we took the cross product of P and Q, and that gave us the surface normal. So nothing's changed, it's all the same. So after you finish that, you've got 8 surface normals for the 8 different polygons along the sides. Also not shown here, you've got 1 surface normal that points to the viewer for the end cap that's closest to the viewer, and then you've got another end cap on the other side with the surface normal that points directly away from the user. So I show 8 surface normals here, 0 through 7, but they're actually 10 because we've got 1 on the end cap nearest you and we've got 1 on the end cap further away. And so I say some nice things about flat shading. And I compare it here to a basic wireframe with hidden surfaces removed, the basic polygon fill where I came up with the colors, and flat shading. And so, you know, from bad to better, right, or from worstest to goodest. If you choose your colors and just fill it like we did in the assignment that you guys did last week, it looks 3D, but it looks cartoonish because there's no, it looks complete, it's not locked into the environment in any way. It doesn't react to the light at all. It's just like you're coloring it in a cartoon, right? But at least with flat shading, you at least it still looks like an octagon that's been extruded into 3 dimensions, because that's what it is. But at least you can tell, oh, the lighting is coming in this direction at 45-degree angle here, right? So that's that. And the worst thing about flat shading is how horrible it is for specular highlights. Remember, we're still using underneath this thing the Phong illumination model that has a specular component to it. Well, basically what happens is either you don't see the specular highlight at all, or the specular highlight is splashed across an entire polygon here. Why? Again, think about what we're doing here. We're getting one surface normal per polygon. So it's like we're getting one sample per polygon of what the lighting situation looks like on that polygon. And then we're just assuming the entire polygon is the same, the color for every pixel on that polygon, and it's the same as that one polygon that you sampled, or that one point that you sampled. Sampling at one point is not is not a lot of samples. And so if the specular highlight happened to hit surface normal is here, well then it would be splashed all across this polygon. But if the highlight happened to hit, say, somewhere over here, you would completely miss the one point that you performed the illumination calculation at, so you wouldn't see it at all. So again, specular is kind of a absolutely the whole polygon's painted with it, or you completely miss it. You might say, well, that's not so bad. But if this thing is rotating in any way, then what happens is your as this thing rotates, your polygons just occasionally flash a very bright color. That's what happens. So flat does a pretty awful job with it certainly does a very poor job trying to hide the polygonal mesh. It basically doesn't. Okay. But it does make it look solid in 3D. The first serious attempt at trying to come up with a shading method to de-emphasize the underlying polygonal mesh was by Henri Giraud. He's still alive. He was born in 1944, so he's getting up there in years, but he's still with us. And he did this in the early 70s. Giraud shading is not that bad. Basically, it starts with the same surface normals that you have to compute if you want to do flat shading. But instead of just flat shading, it says, let me figure out what the surface normals are at the vertices of each polygon. Now, how am I going to figure out what this surface normal is? I didn't compute it directly, but if I've got the surface normals for the adjoining polygons, I can add these vertices, these surface normals together, and then I got to normalize, but I can add them together, and that will give me this surface normal at the vertex, this vertex normal. And I can get this vertex normal by adding this normal to this normal, and I can get this vertex normal by adding this normal to this normal, blah, 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 blah. I can get them all. Okay? You might say, well, big whoop. In flat shading, you had one surface normal per polygon, and now you're going to have one surface normal per vertex. What's the big? Well, it's actually going to be a huge big, because what we're going to do is the following here. We will first, as I just said, compute the surface normals at each vertex making up the object. And I just described how to do that. We're going to do that by looking at the adjacent polygons and their surface normals, add them together and normalize, and that'll give us the vertex normals. Now, we're only showing 2 vertex normals for polygon 0, but remember, we're looking at polygon 0 edge on. There are really 4 vertices because this is a rectangle, right? Remember, when we rotate that puppy, right, you can see that there's front 0, back 0, back 1, front 1, right? That is this top poly, this rectangle that I'm looking at edge on a few pages down. So I have a surface normal here, a surface normal here, a surface normal here, and a surface normal here. So you might say, okay, so now I've got 4 surface normals rather than, or 4 vertex normals rather than just the one that I had under flat. So at least now I'm sampling the lighting at 4 points rather than at only 1 point. Okay, we're sampling the surface normals at 1 point rather than, or at 4 points rather than 1 point. So what do I do with these surface normals that I have at my vertices, my vertex normals? Well, I apply an illumination model, generally the Phong illumination model, at each vertex using that vertex normal. So going back a page or 2 here, where I'll just use this one. Whereas with flat shading, I did 1 point. I figured out the surface normal, which we've done for backface culling and all of that kind of crap, and I applied the illumination model here and got 1 color, 1 intensity that I applied to the whole polygon. But now I'm going to have a surface normal here, which lets me get an intensity calculation, perform an intensity calculation, and I have a surface normal here, so it lets me perform an intensity calculation, and a surface normal here, so I get an intensity there, and an intensity here. So I will get an intensity value at each of the corners, at each of the vertices of these rectangles. And I'll get that for all of the rectangles. Okay, great, but now you just got 4. What are you going to do with them? I'm going to perform a bilinear interpolation of the vertex illumination intensity values in order to paint the polygon with an intensity that varies smoothly across the surface of the polygon. That's a lot of words, but the concept is really simple. And actually, it ends up being exactly what we did with the z-values for our objects to implement the z-buffer. If you'll remember, with z-buffer, we didn't have a z-value for every point on the face of the object. We had an x, y, z, right, at each vertex, at each vertex of the polygon, and then we spread those z values across the face of the polygon to come up with the z values for all of the points that were not at the vertex. Well, we're going to be doing the same thing here, only what we're going to be smearing, like we did those z values, is we're going to be smearing intensity values. Okay, looks like there might be a question or 2 here. Let's see. Andrew asked, do the vertex normals include the end caps? That's a great question, Andrew. When I talk about vertex normals, I'm talking about vertex normals at the vertices of each polygon. Now, we know that polygons share vertices. This whole object that I've created here has has 16 vertices. I know that because I gave them to you, 8 on the front and 8 on the back. But those 16 vertices are shared between 10 polygons. You've got an octagon at the front that includes all of these vertices, and then you've got an octagon at the back that includes all of these vertices. But then the vertices are reused because, like, the top polygon is front 0 to back 0, back 0 to back 1 to front 1. So I'm reusing these vertex points. Vertices can have different surface normals depending upon which polygon they're participating in. What do you mean, Michael? Well, think about this point right here. When I'm talking about polygon 0 and polygon 1, the surface normal for that point right there is the addition of this surface normal and this surface normal. So it would kind of point out at a 45-degree angle in this direction. But when I'm talking about the same point, the same vertex, in regards to the end cap, it's got a completely different surface normal that would point really essentially, well, when it was end on, it would have been 0, 0, minus 1, right? And in fact, if you're talking about the end cap, especially in the orientation that we started with, right? If you're talking about the end cap, all of these vertices, when you're talking about the end cap, are pointing directly at you, right? So a vertex can have different surface normals or different vertex normals associated with it, depending on what polygon you're talking about. So think of the vertex normals as being associated with the polygons rather than the point cloud. Because when we think about the point cloud, we think about each vertex, and it doesn't matter what polygon it's in, etc. But this is more like edges, right? It depends on the polygon. So do the vertex normals include the end cap? The end cap, every vertex in the end cap will have a vertex normal, yes. They will all be pointing in the same direction, all 8 of them. Those same vertices will participate in other polygons, lengthwise rectangles, and they will have different vertex normals in those polygons. Okay. Let's see. Eric says, considering that our meshes didn't previously require any specific order to the polygon list, how do we go about determining which polygons are adjacent for calculating the vertex normal? That, Eric, is an Eric question. That's a very good question. Is it just checking which polygons share vertices? You answered the question yourself. Yes. You just like the point cloud list doesn't give you all the information to draw an object, you have to know where the edges are. You have to know where the polygons are. To do shading properly, to compute those vertex normals, you need to know which polygons are next to which other polygons. And not only which ones are next to which ones, because remember, this polygon, the front cap, is next to this one and this one and this one, all 8 of them. But when you define the object, you have to you basically have to either come up with an algorithm or by hand say, okay, which polygons do you want to blend surface normals between, and which ones do you not want to blend surface normals between? So I don't want to blend the surface normals on the end caps because I don't want it to look like this guy blends in with this guy, because then that would make the end look rounded. I want it to be sharp. So I have to essentially by hand say, no, in polygon front, all of the surface normals point, in the same direction. But for polygon top, this polygon is a blend of these two. Yeah, manually, semi-manually, you can come up with a little algorithm that travels around the that travels around the circumference for the 8 polygons. That's what I did. Basically, if you're at polygon 0, your left 2 vertices are with the previous polygon, right? And your right 2 vertices are with the next polygon. And if they're numbered 0 through 7, you can just write a little routine that goes through and adds them up. So it's semi-manual, I guess you might say, or semi-automated. But yeah, it's not. You do have to know which ones you want to blend and which ones you don't want to blend. That's an interesting thought, Andrew. Even a little bit more simpler, you could take a cube and you could shade the cube as if it were a sphere. It would still look like a cube, but it would be shaded as if it were a sphere. Very interesting. But if you blended here, the end cap, while it would still be flat, would smooth these things so that it'd be brighter over here and darker over here. It would look like a rounded edge if you were looking at it. So it would look like an end cap rather than a flat cut there. But again, the angle, when you look at it at an angle like this, it would still be completely apparent that it was actually really flat. So all we're doing is painting here. We're not changing the underlying structure. Okay. So I did give you the vertex normals for polygon 0. I computed these, and you'll see that the vertex here, basically here are the points: front 0, back 1, front 1, and you'll notice it's interesting because this thing is a cylinder, right? As you go around the edge, this surface normal will always be equal to this surface normal, and this surface normal will always be equal to this surface normal. They don't change along an edge here. And you can actually see that since I give you the numbers for one particular polygon here. And like I said, I computed these by taking the surface normals for polygon 7 and polygon 0 and adding them together and normalizing. And then I computed these by taking polygon 0 and polygon 1. So the first two are polygon 7 and polygon 0 to give me these two. There are actually two here, right? There's one at the front and there's one really behind it on the back, right? So I added up these two vectors to get this one, and I added up these two vectors, 0 and 1, to get this one. You can actually see I did it there. I built a little spreadsheet that implemented this just so that I could see, and that just so that I could build that table without having to use a calculator by hand to get those numbers. But you should get comfortable with that, because when you code it, you need to make sure that your code is actually creating the proper surface normal. So if you went and you did the little calculation in a spreadsheet, verifying that it's right by looking at my answers here, right, then you'll know that your code is actually generating proper vertex normals. Because if the vertex normals are wrong, everything's going to be wrong. So what does it look like? And here, this paragraph, again, you need to, I'm not reading every word that I've written. You need to go back and read every word that I've written here, because there's a lot of important things that I just don't have time to go over every one of them. But this is where I'm talking about the end caps and the fact that their surface normals are different, and I'm also talking about how I computed the vertex normals for polygons 0 through 7. So what does this thing look like? You get if you had a triangle, you would get 3 surface normals. From those surface normals, you would compute 3 intensities, and then you would do a bilinear interpolation where you're computing the intensities along the active edges, and that's given by the delta for the intensity is the intensity end minus the intensity start divided by y end minus y start. That equation should look very similar. It's in your polygon fill, only it's not for intensity, right? It's for z, right? And also moving across, you take your delta intensity on the fill line is the right intensity, the intensity on the right edge that you need to end up at, minus the intensity on the left edge for that fill line that you started at. So that's how much you need to change, divided by x right minus x left, which is how many steps you take. And so that gives you the change across. And you'll get something like this. You can see that it's lighter on this side, and this goes from light to dark here. And as I go across, I'm just blending these things using these 2 equations. So it's very, very similar. Here's the intensity equation. Intensity end minus intensity start over y end minus y start, because it's vertical, right? When you're talking about what is the change in y, when you're talking about the active edges. And when you're talking about going across, you're talking about the change in x. So this is the change from along an edge from fill line to fill line. We have 2 versions of this, one for the left edge. So here's the delta for the left edge. Where do you start at? You start at the intensity at the start point for that edge. How do you change the intensity at each edge? Well, you just take the intensity of the previous fill line and add to it the delta for that edge, and that gives you the intensity for that edge left in this case, at the next fill line. You've got the same 3 sets of equations for the right edge. So now I have now that I have how to get from intensity to intensity along the left edge and along the right edge for a particular fill line, I can go across. And so that's the 3rd set of equations that take you across. Again, these should look extremely familiar because they're exactly the same equations that we were doing with Z, only now we're not doing it with Z, we're doing it with illumination intensities. So the change in pixel intensity as we move across the fill line is the intensity at the right edge on that fill line minus the intensity on the left edge of that fill line over what's the change in X on that fill line. What's the X value on the right edge minus the X value on the left edge. So this gives you how many steps along X. This gives you how much it needs to change. Do the division. That gives you how much you change at each step. Now that I know how much the intensity changes at each step along the fill line, all I need to know is what do you start at? Well, you start at the intensity, whatever it was on that fill line at the left edge. And then how do I get my next intensity value? Well, take my previous intensity value on that scan line, add to it what the delta is along that scan line, and that gives you the next one. It's a bilinear interpolation, exactly what we did for Z. And that's all there is to a Garot shading. And it's actually impressive that this trick looks so good. This is the same cylinder. It's at a different angle, and you don't even see a mock banding effect here. Or if you do, it's very, very, if you don't look directly at it, if you look slightly off to the side, you can see, oh yeah, there appears to be an edge here. It's very, very subtle. If you look directly at it, you often don't see it. If you look a little off to the side, your visual system catches that and go, oh, there's an edge there. Our visual system has in it the equivalent of a high bandpass filter, which enhances edge detection. Probably If you're a creature that's evolving, finding edges from your visual information is quite important to not fall off cliffs or to spot the leopard in the trees or whatever. So our eyes are very sensitive to changes in the rate of change, and that is what there is no edge here per se, but the rate of change here, because we're doing linear interpolations, the rate of change in color here is different than the rate of change in color here, and your brain says, there's a rate of change here, so there must be an edge there. Our brains are kind of cool. I like my brain. I would be lost without it. So here is the specular highlight for Garot shading. You might say, okay, well, this looks pretty good. Actually, it looks pretty crappy because it caught it, but it's spreading that highlight way further than it should be here. But because our cylinder is so simple, it doesn't look too bad. But if you look at a sphere, especially a sphere that is rotating, you get this extremely weird effect here under Garot shading, where when one of the vertices happens to land in the specular highlight, that specular highlight gets swooshed across all of the surrounding. No, I don't want that. I don't want that. It gets squished across all of the surrounding polygons. Here's something pretty interesting about this. I included this in my this little animation that I found on Wikipedia in the Word document. But you know, in Word on my laptop, I'm using an older version of Word, and it's just a still image. But on this laptop that I'm using for video conferencing, it's actually showing the animated GIF as an animated GIF. I imagine that when you look at it on your PDF, that it's going to be a still image again. But I'm glad it's rotating, because this makes the problem totally clear, right? You get these weird flashes as the surface normal, as the vertex normal comes into the specular highlight, and that specular highlight is smeared across these polygons. We're catching the specular highlight here, and it's being smeared across these two polygons, but it doesn't look quite so bad because, one, this is a still image, and two, well, you don't really intuitively know how much should that highlight have spread. But this animation here makes it really clear. Okay, the mock band effect. So that's so what I'm pointing out here are problems with Garot. Specular highlight is a problem with Garot. Mock banding is a problem with Garot. Mock banding is named after Ernst Mach, by the way, 1838 to 1916. And you can see it very clearly in this one because of the way the light falls. It's very obvious that there's a change in the rate of change here. And so your eye sees this edge very clearly and sees this edge here a little less clearly, but you can detect it. And lack of shadowing. These routines of Garot shading, flat shading, and even Phong shading that we're going to talk about don't do shadowing. And the reason why they don't do shadowing is Phong illumination, the underlying fog illumination, doesn't do shadowing. Okay, so let's move on to the last technique, Phong shading. We were just looking at this image, and I was saying how bad the specular highlight is. That's because when you look at it next to Phong, you can see it really does look crappy compared to Phong. In Phong, it's a very tight highlight. Here it's smeared. Here is another example of Phong illumination or Phong shading. And you see that here, because the highlight fell essentially in the middle of this polygon here, neither of the vertices, the normals on the vertices, caught the highlight, so it's totally missing. So with Garot, specular highlight is either totally missing or is smeared across polygons. Phong shading solves that. Phong shading also solves mock banding. You don't get that weird banding effect that you do with mock banding. So how does Phong shading work? Very, very similar to Garot shading, okay? Except in Garot shading, I still have to get the surface normals, and from those I get my vertex normals, so none of that's changed. But in Garot shading, I apply the illumination equation here at the vertices, and what I interpolate are those intensities, and the colors essentially is what I'm interpolating. Phong says, no, let's not interpolate the colors, let's interpolate the surface normals. So I will get a surface normal for every pixel that I'm going to render, and then right before I paint that pixel, I will do an illumination, a Phong illumination calculation for that pixel. And what that does is, you can't change the fact that this polygon is still flat, okay? It's your cylindrical approximation is still an octagon that's been extruded into 3 dimensions. It's a very low polygon object. But I can, by interpolating the surface normals, I can come up with a surface normal for every point on that polygon where the surface normal is very close, if not identical, to what the surface normal is on the underlying actual cylinder in this case. Because I've got a sample here, and I've got a sample here, and I assume that the samples will change at some fixed rate, that the curve is smooth. And as long as the curve is smooth, doing a linear or bilinear interpolation of surface normals will mean that every pixel that I'm going to draw, I will have a surface normal that pretty much matches what the surface normal on the actual cylinder was. And that's why this looks so damn good. It's still just 8 little rectangles. You're only looking at 3 little rectangles here. But as I paint each pixel, I am getting what is essentially the surface normal from the original underlying cylindrical object. And I am using that to paint the spot on the flat polygon. So because of that, unless you're looking at an edge, your eye essentially sees the exact color that it would see at that spot on the original object. And this is pretty friggin' wonderful because it lets us make computer graphic objects look like they're far more complex than the underlying object that we're actually keeping up with. It's a cheat, but it's a fantastic cheat. Okay, let's see. So it's much more computationally heavy for much better smoothing. Absolutely. You might say, well, it shouldn't be that much more expensive because you're just interpolating surface normals rather than interpolating intensity values. That's true. The interpolation equations are no more expensive, okay? But computing Phong illumination is an expensive operation. In flat shading, you're doing that once per polygon. In Garot shading, you're doing that intensity calculation a handful of times, once for each vertex. So if I have rectangles, I'm doing 4 of those calculations. If everything is triangles, I'm only doing 3 intensity calculations. But if I'm doing Garot shading, if I'm doing Phong shading, I'm doing a illumination calculation, an expensive illumination calculation for every friggin' pixel. So it's much more expensive, orders of magnitude more expensive. So it costs more, but it looks nice. So you got to ask yourself, hey man, is this pretty highlight worth about 100 times more computation than this one? You might say, no way in the world. But then I go back and I go back to this epilepsy-inducing animation here and saying, well, how about now? Are you willing to pay 100 times more for an animation in which this would just look like a smooth ball with a highlight on it? And you might go, okay. And then you might say, well, but remember what we're saving here. All of our definition of our object, all of our rotations, all of those things, you're getting away with murder there, because this is only 16 points that you're dealing with when you're doing rotations and scaling and blah blah blah, all of the moving it around. So even though it looks good when you finally render it, all of the math of moving it about the environment is still only happening on 16 points, on 16 vertices there. So you're still saving a tremendous amount. Okay, so what does Phong look like? Well, I've already told you. Phong, well, here's the pseudocode for Phong, and a picture showing you exactly what's going on. We'll start with the picture. We still get the surface normal for every vertex, but instead of calculating the intensities and interpolating the intensity, we interpolate the surface normals along our edges, and then we interpolate the surface normals across our edges. And only when we get to, are we ready to draw the pixel, do we do the illumination calculation. So Phong shading, first compute the surface normals for each vertex of each polygon making up the object. So you have to start with the surface normals for each polygon, and then you put them together the way we talked about for the road to get the vertex normals for every polygon. But then for each pixel to be painted on each polygon, perform a bilinear interpolation of the vertex normals in order to derive the surface normal for the pixel, apply an illumination model to compute an illumination intensity for the pixel utilizing the pixel surface normal, and then paint the pixel with the illumination intensity value. So conceptually, it's very similar. There's one little thing you got to remember. So, you know, the delta of the surface normals are the same. What's the vertex normal at the end point minus the vertex normal at the start point divided by the number of steps in y end minus y start. There's a little catch, of course, because while the y's are scalars, the n's are vectors, and so you got to really remember that it's it's a normal x, a normal y, and a normal z. So they're really three equations here rather than one, because the n is a vector, y is just a scalar. So this gives us the actual change in x, change in y, and change in z. And you have to keep up with each of those three things separately. I will go back and comment about in Garot shading, you only have one intensity if you're not doing RGB, if you're doing monochrome. But actually in my code, it was just easier for me to keep up separately with ambient, diffuse, and specular. And so even with my Garot shading, I ended up with three different things. It actually worked out kind of nice because I just called them A, B, and C. And if I'm doing Garot shading, the A, B, and C are ambient, diffuse, and specular. If I'm doing Phong shading, it's surface normal in X, in Y, and Z. The code is the same. So you got to have, you know, for the left edge, the change in X, the change in Y, the change in Z. Let's say Z equals. This is what happens when you move your life through cut and paste. Oh, the gods don't like me today, do they? So in X and Y and in Z, and then you need the initial start points, which are just what was the end start on the left edge, and then you the end start for at the starting point for the left edge, I should say, and then you get the NX, NY, NZ for the next one from the previous one. So you get it for fill line I plus 1 from what it was at fill line I, plus the appropriate delta. And so that gives you the changes in NX, NY, and NZ along the left edge. It might look like I'm showing you the same page again. Well, it looks like the same page because it has the same friggin' typo in it, doesn't it? But this is the right edge. So you have the left edge and you have the right edge. And then you have to have the starting point for the right edge. It gives you the first fill line. And then you go through and you add in the deltas to give you the start point for the for that fill line. So basically, all of these equations that I just talked about, what they're giving you is they're giving you the change from scan line to scan line, from fill line to fill line. They're telling you where you start, the start point, and then they're telling you how to get the next one from the previous one. You just take the previous one and you add in the delta, and that moves you down the edge. And that's why we had to have the equations for the left edge and the equations for the right edge. The last thing I'm just about to show you is walking across a fill line. The difference there is going to be instead of a vertical Y to get the number of steps, it's going to be the horizontal X that gives us the number of steps. So right edge, left edge, and now across the horizontal fill line, okay, what's the X on the right? What's the X on the left for this fill line? Over how many steps in X do you take? That gives us the delta X for the fill line. You got the delta Y for the fill line. You got the delta Z for the fill line. Finally, I got the Z right there. That's good. And then what about the, how do you get started? Well, whatever the normal is on the left edge for this fill line, that gets me started. How do I get the next one on that fill line? Well, I just take the previous one on that fill line. So I get pixel J plus 1 on fill line I from pixel J on line I, and I add in how much X changed along that fill line, and then how much Y changed along that fill line, and how much Z changed along that fill line. It's exactly what we did for Z's. And then we end with a beautiful Utah teapot. It's just a pretty, and I had a little extra space on this page, so I said, I'm going to put a Utah teapot there. The Utah teapot is a classic object. You can probably find a polygonal mesh for it online somewhere, and that's nice. Eric asks, so are these calculations able to be parallelized on a GPU, or does this have to be CPU calculated? They can be parallelized on the GPU. Sure, they can. In some sense, if I'm calculating the next thing from the previous thing, I have to have the previous thing. So in some sense, it is sequential, but you could be doing all polygons in parallel, right? So it's still quite parallelizable. But if you're using this for a particular polygon, the way these algorithms are set up, they are using the previous to get the next. So they are, in a sense, sequential. That's a good question. Let's see. Next up, what do I need to do? I need to quickly go over the assignment. Okay, so we're going to be doing lighting and shading. It's due a week from tomorrow. So you have, since Mardi Gras is pretty much canceled due to COVID, and you're going to be stuck without any parades, got plenty of time. Just recapping what's in the chapter to show you how beautiful Phong looks and how middle of the road Garo looks and how terrible flat looks. I reproduced well, actually, I stole this when I rebuilt it for the text, and I never changed it here, but I grabbed this off the internet. I redid it myself and for text. But anyway, that's our octagon that we extrude to, after you rotate it, give us this. So I'm giving you guys the object. I'm giving you in fact, if you go to the last page, I give you all of the vertices, I give you how to put them together in the polygons, and then I give you the definition of the cylinder. So this looks very similar to what we've been using all along. So you got the object free. I gave it to you for free. What do you need to actually do? Well, it's pretty obvious what you need to do. You need to implement flat shading, Garo shading, and Phong shading. Basically implement the monochrome Phong illumination. Actually, this is fun. You should use the monochrome Phong illumination model that was presented in the 20 spheres example code as a go-by. So this sentence is screwed up. But I'm basically saying, hey, I've given you the Phong illumination model in the 20 spheres example. And there's a lot of good stuff there because you're going to need to have that illumination model. The model contains 3 separate components, obviously, the ambient, the diffuse, and the specular. Use the following keyboard digits to select the rendering mode. So the rendering mode will be flat shading. I guess actually what I'm saying here is that you need to implement the Phong illumination model because that's going to be used by shading. So I guess the sentence isn't wrong here. You will implement the Phong monochrome Phong illumination model using the 20 spheres example code as a go-by. So you're going to need illumination to be able to do shading. And I'm telling you, basically, I've already given you 90% of the illumination, 100% of it in the 20 spheres example that's in your mini text. Okay? But once you've got that, you're going to implement flat, Garo, and Phong. I just added that. I'm not going to regrade whether 1, 2, and 3 are still working. My code ended up looking kind of crappy because polygon fill was already tweaked to work with colors that the user gave, right? So I created, instead of polygon fill, I think I call it polygon shade, which is the polygon fill algorithm where I tweaked it to work with the additional parameters to be able to do a proper shading. So there's a lot of old code in mine. I'm not going to test 1, 2, and 3. So if you want to eliminate those to simplify your code, you can. I actually found it kind of helpful to have it all there because I had a working version of polyfill that I could copy to make my polyshade. from and then start tinkering with it. And if things ever went wrong, I had a polyfill that was still working. So I could say, oh, Mike, what did you screw up? Oh, yeah, you changed that. You shouldn't have. So it ended up with crappy code in a way, but it was actually sort of helpful because I always had a run and go by in my code. It's up to you. I'm not going to grade 1, 2, and 3 again, but you should map 4 to flat, 5 to Garot, and 6 to Phong. And I'm only going to be interested in, we've got multiple objects down here in 1, 2, and 3, but when I go to flat, Garot, and Phong, I'm just using the cylinder. So if you want to leave the other objects on the screen, you can, or you can just not paint them. Because I am not going to test, for example, does your Z buffer still work with the shaded cylindrical object? The answer is it should. If you didn't screw it up, if you didn't change it, it will. But I'm not testing you on that. I'm testing you on do you have the shading algorithms working? So that's really it. This next point just redefines what flat shading is, what Garot shading is, what Phong is in a little quick summary that goes back and summarizes what we were just talking about. I talk a little bit here about how you compute the surface normals. For the 8 longer sides of the cylinder, polygons 0 through 7 inclusive, each vertex normal will be computed by adding the surface normals of the 2 sides that share that vertex. Using the orientation in which the cylinder is defined, the left 2 vertices of polygon 0 abut polygon 7, the right 2 vertices of polygon 0 abut polygon 1. In general, each of these 8 polygons, the rectangles, abut the polygon to its left and the polygon to its right. The vertices of the 2 end polygons of the cylinder, those octagons, should not be blended. Each vertex normal will simply be the surface normal of that octagon. Always remember to normalize your normals to unit vectors before computing dot products, because the vector addition will result in vertex normals that are not unit vectors. So this kind of gets at Andrew's question of, well, do you have to do it by hand? Well, no, I said it's semi-automated. This just describes how to compute it with a little bit of code rather than by hand setting them. I'll leave it to the developer to come up with the constant of diffuse reflectivity, the constant of specular reflectivity, the spec index, etc. But use the values that I gave you in the 20 spheres example. That's what I did when I ran mine. Remember, the light source is coming in at a 45-degree angle over the user's right shoulder. So in our left-handed system, that would be 1, 1, minus 1. Note that 1, 1, minus 1 is not a unit vector. You would need to normalize it. Additional requirements, do it all yourself. None of those have changed. How do you turn it in? You email it to me. Please follow the way we've talked about doing that in the past. Are there any questions? There seem to be a couple here. Do we need to add the octagonal prism to our current shapes or replace them with it? I think I already addressed that. It's a new shape. You can get rid of your old ones if you want to. My brain read that as, do we need to AD? That's cute. Bonus points if we shade the other objects too. How about respect points, Andrew, if you shade the other objects too? The other objects, though, like the pyramid, is not a rounded object, so it wouldn't end up looking any different than flat shading because the sides are all flat, right? Now you could take a pyramid and paint it like a cone, right? By blending those vertices. Okay, I see we're over time here by a minute, so I'm going to call it a day here. We'll stick around if there are any questions. I'll be happy to answer them. But anyway, I'll see you guys on Friday. Remember, you do presentations on Friday.